Fluid machinery relies entirely on physical geometry. These are massive momentum harvesting engines, and the exact path the water takes dictates the governing physics. For over a century, the industry default for reaction turbines has been the Francis turbine design. This diagram shows a Francis turbine. Its defining characteristic is right here, inward flow. Water travels from the outer perimeter, squeezes through stationary guide vanes, and transfers momentum into the spinning orange rudder. Finally, the fluid drops axially into the draft tube below. This outside-in trajectory forms standard boundary conditions assumed in most baseline fluid dynamics problems. Diagnosing alternative turbine designs requires first mapping out this inward flow baseline to recognize the impact of different geometric configurations. The outward flow reaction turbine presents a different configuration, a structural inversion of the standard Francis model. Instead of entering from the perimeter, fluid is injected centrally along the main shaft axis. In this cross-section, a stationary guide wheel surrounds the central shaft. Water begins its journey here in the center. Horizontal red dashed arrows show the fluid forced radially outward from the guide wheel, moving away from the center into rotating runner channels. Because water moves outward as the machine spins, centrifugal force inherently assists the flow direction through the blades. This creates a critical geometric rule, visible here in the dimensional brackets. The inlet diameter, d1, is strictly smaller than the outlet diameter, d2. Reversing flow direction across these radii forces a recalculation of how blade speed interacts with the fluid, necessitating a distinct mathematical model. To extract actionable data from this architecture, specifically torque and mechanical power, we must translate that complex three-dimensional fluid motion into a solvable two-dimensional model. The standard kinematic tool for resolving these fluid structure interactions is the velocity triangle. By using vectors, we can precisely map both the speed and the specific angular direction of the water as it hits the moving metal. This is a top-down view, isolating just one curved stationary guide vane segment, feeding directly into a single curved runner blade. We have two critical boundaries for our analysis: the inner tip where the fluid enters, and the outer tip where it exits. The exact relative angles of the fluid at these two specific boundaries will dictate whether the machine effectively generates power or if it's just uselessly turning water. We will build the math starting at the smaller inner boundary, d1. First, draw absolute velocity v1 at angle alpha, then tangential blade velocity u1. Subtracting them gives relative velocity vr1 at angle theta. Breaking v1 into orthogonal components gives radial flow velocity vf1 and tangential whirl velocity vw1, representing rotational momentum. Calculating this precise inlet triangle dictates the exact angle at which manufacturers must cast the steel blades. Get this wrong, and the water smashes into the metal, causing violent, turbulent shock losses right at entry. Now we shift focus to the outer boundary, d2. Remember the fundamental rule of outward flow geometry. Because the fluid is now at a larger radius, the metal blade tip here is moving significantly faster than it was at the inlet. The outer tangential velocity vector, u2, is drawn much longer than u1. The water exits as relative velocity vr2 at angle phi. Adding vr2 and u2 gives absolute exit velocity v2 at angle beta, which breaks down into outlet whirl velocity vw2 and flow velocity vf2. The size of this final absolute velocity triangle is critical. It represents residual kinetic energy lost to the system, energy that simply washed out of the turbine without being converted into shaft power. Let's look at both completed velocity triangles side by side. Out of all these intersecting lines, the turbine's actual power output relies almost entirely on just two vectors, the inlet whirl velocity, vw1, and the outlet whirl velocity, vw2. This leads us directly to the torque proportionality equation, derived from Euler's turbine theory. Torque is derived strictly from the difference in angular momentum between the fluid entering the runner and the fluid leaving it. Maximizing rotational momentum at the inlet, vw1, while designing the runner to minimize the remaining momentum at the outlet, vw2, yields the highest possible mechanical efficiency. These geometric constructions function as direct, calculable predictors of a hydroelectric plant's exact megawatt output. So how do we apply this theoretical model to actual numerical problem solving? The single most common error in kinematic analysis is misassigning the inner and outer peripheral blade velocities. If you treat this like a standard inward flow Francis turbine, you will plug the larger velocity into the inlet side of the equation. In an outward flow model, doing that violates the machine's physical boundary conditions. Look at the flow path in this diagram one last time. The water starts in the center and moves radially outward. Accurate mathematical modeling always requires verifying the physical reality of the machine. For outward flow turbines, the inlet is small, the outlet is large, and your vectors must scale accordingly.